We are now going to put together most of the calculus that we have been doing with inflection points and your critical numbers to sketch the curve without a calculator. So if I want to sketch any function without a calculator, you're going to use all this information on the front of the sheet to do it. Okay, so there's nothing really new here. It's putting some of the stuff we did last year with the calculus that we've done this year, and then put it all together and see what the curve looks like. Some of these functions are a combination of a square root function and a rational, so we don't know what they look like without doing this, and obviously without using a calculator, but that's no fun. So I'm just going to go through, I'm going to explain what each thing is and how to do it, kind of review that for you, and then I'll probably just do one or two of the problems, and we may use some of these as practice later, but I don't think I need to do every single one out. Once you get the idea, it's just going to be the algebra and the calculus involved in all of the different functions. Okay, so domain. How's that going to help you? Because first we need to know what is the domain of the function. Okay, so we remember that obviously your domain are all your x values. Things you have to worry about is the denominator can't be 0. That's, one restriction. And other thing, your radicand inside, I'm going to actually write radicand, whatever's inside the square root has to be greater than or equal to 0. Okay, so those are really the two restrictions that we have to worry about. Your intercepts, you want to find both x and y. Okay, well, how do you do that? Obviously, to find your y-intercept, set x to 0, so plug in 0 for x. To find your x-intercepts, set the equation, so set y equals 0 and solve for x. Okay, so those will help us. Symmetry, this will help us. If we know it has symmetry, if it's an even function, we know, hopefully we remember, that it's symmetric over the y-axis, so that will help us when we sketch it. And if it's odd, I know it's symmetric over the origin. Now, how do you test for this? If you plug negative x into the equation and you get the exact same thing, it's even. And if I plug negative x into the equation and I get the opposite, it's odd. Some basic x squared's even, x cubed's odd. Okay? And then if we're talking about sine, cosine, tangent, where I have a periodic function that just repeats over and over again, where this I'm not going to really worry about too much, where f of x is really just f of x plus p. If I continue to add, say, pi, or with sine, x plus 2 pi, if you just keep adding 2 pi, you get the same thing. That's not going to help you that much, honestly. All right, asymptotes. Asymptotes, see if we remember. So horizontal asymptotes is your rule, okay? You compare, so if I have a rational function with horizontal, a polynomial in the numerator, polynomial in the denominator. If the numerator is greater than the denominator, I don't have any. If the numerator is less than the denominator, y equals 0. And if they're equal, it's going to be y equals the leading coefficient divided by the leading coefficient. Hopefully you remember that, and this is just a quick review. Okay. We also know with horizontal asymptotes that if I take a limit of the function as x goes to positive or negative infinity, whatever the number I get is your horizontal asymptote. Okay. Vertical asymptotes are when denominator equals 0, which your limit statement, as x approaches the asymptote, the function would either go to positive or negative infinity. Okay, so in this limit statement, y equals L is your asymptote. Over here, x equals A is your asymptote. Okay, slant asymptotes, you only have a slant, remember this from last year, is if you have a rational function and the degree of the numerator is 1 more than the degree of the denominator. And degree of numerator is 1 more than degree of denominator. 1 more, than degree of denominator. So I have 5x cubed and I have x squared. I could have other things going on here, but that would have a slant asymptote, okay, because the numerator's degree is 3 and the denominator's 2. How do you find it? I would do long division. I would divide the denominator into the numerator Whatever I get is your slant asymptote. Okay, now interval, where how do you find where it's increasing and decreasing? Well, this is the calculus. Okay, so how do you do that? Well, you should know quickly, I'm increasing where the first derivative is positive, and I'm decreasing where it's negative. Okay, how do I find local max and mins? Well, what are you going to do? You're going to use your first derivative. So where f prime changes sign, S-I-G-N, I have a local max or min. Okay, if I go from positive to negative or negative to positive at a critical number. Okay, concavity, what are you going to use to figure out if it's concave up or down? The second derivative, so second derivative is positive. I'm concave up. And if the second derivative is negative, then I am concave down. And that will help us. Where the second derivative is 0 are your inflection points, or does not exist, and that's where I change concavity. And then you're going to take all this information and we're going to actually get a sketch of the curve. Okay, hopefully most of that was review. Now, let's do one. Okay, so the first one's a rational function. So I can go through everything. Okay, I'm going to try to fit it all on here. So the domain of this. Domain, you're looking at what? The denominator couldn't be 0. So x can't be 1 or negative 1. So my domain would be negative infinity to 1, or to negative 1, or negative 1 to 1, or 1 to infinity. That's x can't be plus or minus 1. Okay, so there's my domain. Next are my intercepts. Okay, so my intercepts. To get my y-intercept, plug 0 in for x, and I get 0, 0. And my x-intercept would also be 0. Okay, so again, intercepts. I plugged 0 in for x, so I'd have 2 times 0 squared minus 1. So I get 0 over negative 1, which is 0. So 0, 0. How would you get your x, and that's your y-intercept. Your x-intercepts, you'd set the equation equal to 0. When does a fraction equal 0? The numerator. So I would solve that and I get 0. Okay, so that's my intercepts. Symmetry. I want to test for symmetry. So if I plug negative x into the function, so for symmetry, you could keep organized on your sheet. If I put negative x in for x, what happens? Okay, well, it becomes 2x squared over x squared minus 1, which is the exact same thing. So I'm even, so I have symmetry over the y-axis. Okay. Asymptotes. So if I look at this, horizontal, the degree of the numerator equals denominator. So y equals 2, because it's just 2 over 1, leading coefficient over leading coefficient. And vertical would be 1 and negative 1, because that's what makes my denominator 0. Okay. If I wanted to make a limit statement for that, my limit as x goes to infinity of my function is 2. That's my horizontal limit statement. And then I'd say the limit as x goes to, negative 1 of the function is negative infinity, and I'd have to figure that out if it was going up or down. And the limit as x goes to 1 of the function is infinity. Okay. Next, intervals of increase, decrease. So now this is where we find our first derivative and figure out where it's positive and negative. Okay. So find f prime. Go ahead. I know you guys do this when I tell you to do this. I don't think you ever do, but pause it. Go ahead and find the first derivative. I'm just going to tell you what it is. I'm not going to show all the work. Okay. So there's the first derivative. I can make a sign chart. Okay, so I'd have 0 as a critical number, 1 and negative 1. Why all of them? Because 0 makes the numerator 0, so that's an actual 0. And 1 and negative 1 makes it undefined. So those are also critical numbers. I'm going to label this f prime, and I'm going to plug numbers in. I'm going to plug negative 2 in, plug negative 2 in for x here and here, and I get a positive. I'm going to plug negative 1/2 in, I also get a positive. I'm going to plug 1/2 in, should get a negative and negative. Okay, so what's this telling me? This is saying that I'm increasing from negative infinity to -1 or -1 to 0, and I'm decreasing from 0 to 1 or 1 to infinity. Now what happens at -1 and 1, we know we have asymptotes. That's why they're not included, because we found that already. Okay, and then the last thing to figure out your concavity is find the second derivative. So second derivative, sorry I'm a little messy here, hopefully you're following. Okay, I find the derivative of the first derivative, and you should get 12x squared plus 4 over x squared minus 1 to the third. Okay, do the same exact thing. Make a sign chart for your second derivative. So I have 1 and -1. Numerator never equals 0 because I'd get imaginaries, guys. Denominator would be 1 or -1 would make this 0. So that's also values that I want to include. Okay, and now what am I doing? I'm testing region. So test -2 should get positive. Test 0 should get negative and positive. Okay, so what does that mean? That means I'm concave up from 0 to -1. I'm concave down in between, and I am concave up from 1 to infinity. Okay, so now I just want to actually sketch the graph from all this information. I don't really want to erase everything. I'll erase my limit statements, and I will put my sketch down here. So now I want to put everything together. Okay, so what do we have? We have asymptotes at 1 and -1. Okay, we have a horizontal asymptote at 2. I have my intercept of 0. Okay, now I know from negative infinity to -1, I'm increasing and I'm concave up. Okay, so I'm increasing concave up. There's my part. Now how do I know it's not down here? First of all, because it wouldn't be increasing. And second of all, it doesn't have another x-intercept. Okay, now the middle. What's the middle doing between -1 and 1? Okay, so between -1 and 1, well, between -1 and 0, I'm increasing. And then 0 to 1, I'm decreasing. And the whole thing is concave down. So it must look like that. Increasing, decreasing, and the whole thing is concave down. And then over here, okay, greater than 1, I'm concave up, and I'm decreasing. So I must be decreasing, concave up. Now we could get that we did this last year. We sketched this last year just based on asymptotes, and then we plugged a couple numbers in. But now using all the stuff from calculus, I get a, I could do the same thing. Okay. What I think I'll do for the second one is just, again, go through a little bit of this information. You get the idea. The hard part's just going to be all the algebra and then putting it together on your graph. Okay, so using the increasing, decreasing, and where it's concave up and down. Okay, where the first derivative obviously is positive, negative, all that good stuff that we have to worry about. Okay. All right. I do want to say that I don't have any inflection points because this doesn't change from concave up to concave down. So an inflection point is where the second derivative equals 0, where I change concavity. Okay. All right. And number 2. So we don't know what that looks like because it has a radical in the denominator, but I could go ahead and do everything. So my domain, the inside the square root has to be positive and not equal to 0 here. So it would just be, -1 to infinity. -1 to infinity. Okay. Next are my intercepts. Okay, so intercepts, if I plug 0 in for x, you get 0 over 1, which is 0. If you set the numerator equal to 0, you also get 0. So again, I just have 0, 0. If I plug -x in for x, let's see what happens. Nothing. It's not the same thing, and it's not the opposite. Okay, it's not the exact opposite equation. and it's not itself, so I have no symmetry by testing negative x. What's next? Asymptotes. Asymptotes. So let's see, I know I have vertical asymptotes at -1. Why? Because that's what makes the denominator 0, and I have no horizontal. This isn't a rational polynomial function. Okay? Now you're going to do first derivative. Again, I'm just going to give it to you. You would do this out, okay, and simplify it, which I'm guessing this is going to be the confusion, is some of the algebra here. There's my first derivative, okay? I'd go do a sign chart for my first derivative. What would my numbers on my sign chart be? If I look, I would have the numerator would be 0 here. Okay, and I have -4/3, but the domain is just -1 to infinity. So -4/3 I'm not going to include because I'm -1 to infinity. Down here, -1, but again, I'm not including -1 in the domain, so I don't include it. So I just have 0. And if I test, I get negative, positive. So if I plug in a number here and here, so I know what? I'm decreasing to the left of 0 and I'm increasing to the right. Second derivative comes out to be the quadratic in the numerator, and that is your denominator, okay? So I want to set the numerator equal to 0 to figure out if I have an inflection point. So, and when you set this quadratic to 0, it gives me imaginaries, so I don't have any points of inflection, okay? So there are actually, it's not changing at all, which means what? So it's not changing concave down, concave up, so it must be one thing the whole time. And if you look, this will always give me positive numbers. For -1 to infinity, say you plug 0 in, you have 8/4. So this is always positive. So I'm always concave up. Okay, so put it together. I have an asymptote at -1 and I cross at 0. And I know that I am decreasing to the left of 0, increasing to the right, and I know I'm concave up the whole time. So it must look like that. I don't know exactly what it looks like if this increases faster, but I just want to sketch. So pretty simple, kind of looks like a parabola, but it's not going to have the symmetry of a parabola. And there's the sketch. Okay, so I'm not going to do any more of these. You get the idea of all the information you're going to use to create the sketch.